All right, now let's take a look at how we would figure out the electron configuration for an element that's a little bit more difficult. And the one we're going to look at, randomly chosen, is tin. Its number is 50, so that's how many protons it has. Remember that protons determine the identity of an element, so it has 50 protons. But in a neutral atom, it also has 50 electrons. So we'll just keep that in mind, and we'll write that over here. So Sn, it has 50 electrons, just to keep that in mind. Now remember, the lowest energy level orbitals are going to get filled first. This is always the case. So we're going to start with the 1s orbital. 1s, and it's going to get completely filled. Remember, s orbitals have 2 electrons. Then we move down into the next energy level where you have 2s orbital, again with 2 electrons. And then on the second energy level, we also have the p orbitals. So 2p, 6. Remember that the p orbitals can hold 6 electrons. That level, that energy level, is now completely filled, so we moved to the third energy level, 3s. Again, we have 3s2. And then we also have 3p6. Now that energy level is filled, so we're going to move down to the 4s. So I'm going to start over here, 4s2. And then, as we continue going along this period, we get into this D block. And remember that the D block, its energy level number, the number that comes in front of the orbital, is 1 less than the period number. So even though we have 4s2, this is going to be 3d. And since there are 5 different types of d orbitals, there can be a total of 10 electrons, which, if we look, this one, number 21, would have just 1. This one would have 2. This one would have 3. Chromium would have 4. Manganese would have 5. Iron would have 6. Cobalt would have 7. Nickel would have 8. Copper, this is copper, it would have 9. And then zinc would have 10. So as you go through, that is your total number of electrons that you would find in the d orbital. And since that is completely full, we're going to have 3d10. And then we go back to the 4p. Okay, so keep that in mind because that can get tricky for some folks. The s orbitals and the p orbitals, their energy level is always going to be the same as the period number. Okay, so we have 4s here and we have 4p. It's just that in between those, we have to remember the 3d. So 4p, and since it's completely filled as well, we have 4p6. And now we're going to go down to the 5th period, and we're going to start with 5s2. And then we have all of the d, or the 4d orbitals filled, so 4d10. And then when we get into this p orbital, we're back into the 5p orbitals, but we only have 2 electrons, so it would be 5p2. And you can count them up, and I'll show you a real simple way of counting them up by separating it into tens. So the first 3 here, that's 10. 2, 2, 6 is 10. And I split this up in a difficult way, but 2, 6, 2 is another 10. 3d 10, that's 10. Here you have 10, and that's 10. So total of 50 electrons, which is exactly what we wanted. Now, in class, I also showed you noble gas configuration or noble gas notation, and I want to show you how to do that for really any element. So let's look at tin again. So we know that it's going to go all the way up to 4d10, 5p2, okay? But noble gas notation allows us to eliminate a great portion of all of this configuration. So what we do is first we have to identify the noble gases. The entire right-hand column, or this family, and this actually does include helium as well, but helium, neon, argon, krypton, xenon, and radon, these are the noble gases. Okay, so with noble gas configuration, certainly something is going to be done with these noble gases. When we look at tin, number 50, the first thing you want to do for noble gas configuration is determine which noble gas comes before tin. So it has to be the first noble gas going backwards from number 50. So you would go all the way down and then up to, so all the way across to the left and then up one to figure out what the noble gas would be. So the noble gas before tin is krypton. And so when we do that, we write Kr in brackets. And then instead of having to go through 1s2, 2s2, 2p6, all of that beginning stuff, we can just start with krypton. After krypton, we go to 5s2, and then we do 4d10, and then 5p2. It's really the exact same thing that we did here. It's just that everything up to krypton we eliminate. And that means that everything through 4p6, that's right here, we have eliminated. This noble gas configuration, the 1s2 all the way to 4p6, is the noble gas configuration, or is the electron configuration, excuse me, for krypton. So what we're saying with this noble gas configuration is that it's everything that's the electron configuration for krypton plus these is going to be the electron configuration for tin. So make sure that you are watching out for any time I ask for the electron configuration, which would be the long one, or the abbreviated or noble gas configuration, which is going to include the previous noble gas for each element. So let's try one more, and this time we'll do lead. Lead is, and I'll do it in different colors so that you can tell, lead is Pb. Again, don't ask why, the lettering is a little silly. Lead has 82 protons, therefore it has 82 electrons in its neutral state. So again, you start with the very lowest energy level orbitals. So we're doing Pb, and it has 82 electrons. And I'm going to go through 1s2, 2s2, 2p6, that's 10 electrons, and now we're up to neon. Then we have 3s2, 3p6, that's up to argon. Now we have 4s2, 3d10, 4p6, now we're up to krypton. 5s2, 4d10. Now notice we're going to go past 10, which is the one we just did, and we're doing 5p6. Now we're similar to xenon. And we're going to go down to the 6th energy level, so we've got 6s2. Now, the thing to remember with the 6 and the 7 energy level is that now you have to insert this F block. Remember that F block is inserted here, and while it can be a little strange, you really do just say 6s2, then 4f14. Remember, there are 7 different types of F orbitals, therefore you can have 14 electrons. And once you're done with the 4f14, then you go back to the 5d10, and you finish off with 6p, and it's going to be 1, 2, so 6p2. And you can check, you can count those numbers up and make sure that there are 82 electrons. So 2, 2, and 6, that's 10. 2, 6, 2, that's 10. Here we have 10, so that's 30. 36, 38, 48, plus 6 is 54. Plus 2 is 56. Plus 14 is 70. plus 10 is 80, and plus 2 is 82. So that is your electron configuration for lead. But how would you do the noble gas configuration for lead? Again, you're just going to figure out what is the previous noble gas before lead. Going all the way to the left, and then the one before 55 is 54. So that is xenon. So you're going to put that in brackets. And then you start with this energy level, this 6s2. So really, the only thing that goes into the noble gas configuration is the 6s2, 4f14, 5d10, 6p2. So here you have your full electron configuration, and here you have your abbreviated noble gas configuration. Keep in mind that any element that is on these two periods, in the 6th or 7th period, you have to remember the F block. Don't forget those. And really, if you count up all of your electrons, all of your exponents, and you had forgotten your F block, then it won't add up correctly. So just keep an eye on that and make sure that you count up all of your electrons just to check and make sure. Okay, we'll do more practice on this in class.